All right, in front of you, you should have some extra notebook paper and also the Day 6 notes polynomial examples. All right, let's get started. Number 1, which one of the following is not a root of the equation 10x cubed minus 11x squared minus 47x plus 30 equals 0? And our answer choices are as listed. The first thing is you're going to put your polynomial function into your calculator into y equals. And then I use second window, which what that does for us is it allows us to set the table in exactly the way that we want to do. So you should have this screen, and notice that I have independent, which is the x variable, as ask. And that allows us to put any of the numbers that we want to in there. And as you can see, we have 4 choices, so I want to put those 4 choices in to see which one, is going to provide the right answer. So then when I put second graph, I end up with my table, and I can enter in the -2 and the 0.6 and the 2 and the 2.5. And notice that which of the following is not a root is obviously x equals 2. So I would pick C for my answer. All right, second. The graph of the function f of x equals x minus 1 times x plus 3 cubed times x minus 5 squared. We need to figure out which one of these is true here. We've talked about in class the fact that when we see no exponent on the top of the x minus 1 there, it's understood to be a 1. And that means that we have a single root right up here related to that. And we have a triple root and we have a double root. So we already should know some of the things that we're going to talk about here. So let's go forward. We're going to graph. And when I go to a Zoom 6 screen, I notice that it looks a little different than we're used to. And so I'm going to maybe try to get a different window. And so I reset the window as is shown. Pause if you need to. And then I graphed. And then I see something a little bit odd going on right over here. Remember that what's supposed to happen is I'm supposed to have a single root at x equals 1. Well, that definitely looks to me to be happening there. But then I have a triple root happening at -3, and that one looks a bit cubic there. I would go with it. But at x equals 5, we should be looking quadratic, and unfortunately our calculator has not provided us an option that looks quadratic. So I went ahead and went into my table to kind of get a view of what's happening at x equals 5. And so I made my table setup this time again while we used second window. I made it automatic this time and looked near 5. And I noticed that we were above the x-axis and we were back above the x-axis, which indicates to me that that comes down and touches. All right, so let's see what we can figure out. We expect to cross, or in the words of this question, cut the x-axis at 1. And we should also cut the x-axis at -3, but we should sit on it at 5. All right, so that one would be cuts, I think I pick C again. Cuts the x-axis at -3 and 1 and touches at 5. Third one, which one of the following is the root of the equation? Again, I put into y equals and tell my calculator to use the table to help me figure out which one of those is the root. And out of -2, -1, 1, and 2, I see that the one that produces a 0 is at x equals 2. Now let's talk about a word that we haven't used before, multiplicity. We have talked about that when we have a squared, that graph tends to look like quadratic there. That's called an even multiplicity, meaning we are going to have a double root there, an even number of roots there. And an odd multiplicity would be that power of 3 tells me that we are going to look cubic there, or has an odd multiplicity. Finally, complex roots, when we're talking about them, those are the things that we've learned that are have a real part and an imaginary part. Back in Algebra 2, those were like 1 plus I, 1 minus I, 2 minus 3I, 2 plus 3I. Note that complex roots are always going to come in pairs. So if I have a degree 1 function, it will have 1 root. Okay? If I have a degree 2, we have a total of 2 roots, and so on. But notice over here the possible combinations. The only way we can have complex roots is if we can have at least 2 of them. Notice they're all even numbers. But also notice that we have to add up to the total number of roots that we've got there. So if this is degree 3, for instance, degree 3 should have 3 reals, or it could have 1 real and 2 complex, and so on. Let's look at this example. A polynomial has a degree 5. Which of the following is not a possible combination for its roots? 5 real roots, 1 real root and 4 complex, 3 real and 2 complex, and 2 real and 3 complex. First of all, I check to see that they each add up to 5 total, and they do. 5, 5, 5, and 5. But the problem is right here, this one has 3 complex roots, when it should have them in pairs, 2 or 4 of them, or so forth. All right, let's see if we can sketch a situation. If I can get my pen to work. All right, so if we're sketching the graph of a cubic polynomial, we would start with maybe an x and y axis, and we want to figure out the possibilities of our cubic. We've learned that cubics could either look like this, or they could look like this. And I am not telling you what the coefficient is, so either one of those possibilities would be okay with me. So I'm going to choose the positive leading coefficient one. Okay. And so we want 1 double root and 1 single root. So there's a single root, and there's a double root, and it looks cubic, has 3 total roots, and we can definitely sketch that situation. Next one. Sketch a graph of a quartic. If our graph is going to be quartic, we often have a W or an M looking graph. Remember that the end behaviors will be the same with a quartic because of the even power on it. So let's see if we can have a negative leading coefficient. So that means we have this one. So we're going to be opening upside down. And 2 double real roots. So let's see if this is possible. If I came up and there's 1 double root, and then I come across here and there's a second double root. We're opening down, we are quartic, we've got 2 double roots. Third situation, sketch the graph of a quintic or quintic, that's a degree 5, with 4 distinct real zeros. Now it's going to be degree 5. Degree 5 means we have to have 5 total roots. So if we have 4 distinct real zeros, we've got to cross over 4 times. All right? So we can't ever come back up again. And I'm looking at that and realizing with my 3 bends that this one is a degree 4. So there is no way to be able to get a degree 5 with 4 distinct real zeros, because that would only leave 1 complex or imaginary root. And you cannot have just 1 of those, just like I talked about. They have to be 2 or 4 or 6 of them. They come in pairs. Sketch a graph of a quintic again with 1 double root. Again, we could have opposite end behaviors with it being degree 5. So let's start with 1 double root, okay, 1 single root, and 2 imaginary roots. So we've definitely got 1, 2, 3, 4 bends, so we could have a degree 5. we've got the double root there, the single root there, and then never again do we touch the x-axis. So that one looks good to me. Which of the following is a root of the equation x cubed minus 3x squared plus 4x minus 2? All right, so let's talk first about the possible rational roots that we've done in the previous lesson. So remember that we take these factors of -2 and the factors of 1 and make ratios out of them. So we either could have a root of plus or minus 2 over 1 or plus or minus 1 over 1. Now I'm going to take and guess which one might be possible. And if I put in 1 in here, plug in 1 and cube it, and plug it in there and plug it in there, I end up getting a 0 out of that. So now we're going to synthetically divide like we did in the day 5 notes and figure out what we get when we do that. So I'm going to put 1 in here. And coefficients, 1, -3, 4, and -2. And then I do my synthetic division. And then I have what's called the depressed polynomial. So the depressed polynomial is x squared, because 1 degree less than the beginning power, minus 2x plus 2. And now I'm going to use quadratic formula to allow me to get the final roots of the equation. So I've got the opposite of b, plus or minus the square root of b squared, minus 4 times a times c, all over 2 times a. Now as we simplify this, we get 2 plus or minus the square root of, this is 4 subtract 8, which is -4, all over 2. And remember from your Algebra 2 days that the square root of a negative number involves an imaginary number. Square root of -1 equals I. So square root of -4 should be 2i. And then if we simplify, canceling the 2 out of each term, I get 1 plus or minus I as the other 2 roots. So that means we have 1 real root and 2 imaginary roots. And looking up here, the imaginary solution that is what we got was the 1 plus I. All right. Now you should pull out your worksheet, and I will start another video where we will work through some of these problems.